All right. So what we're going to do, we're going to at least get through chapter 3, section 1.3 and 1.4, make hopefully some good distance in the 1.5, and we'll have to finish 1.6 later and on Wednesday. So we should finish chapter 1 by Wednesday, hopefully. So the next thing to get into trigonometry, we talked about angles last time, and we talked about the unit circle, kind of where the unit circle comes from. We talked about how if you take the unit circle and you have a point on that unit circle, well, a point on any place of the xy plane is an x-coordinate and y-coordinate. Well, when you're on the unit circle, the x-coordinate has a special meaning. That's actually the cosine of theta. So just real briefly, if you've got your circle, got your x-axis, got your y-axis, you have a radius of 1. This is an angle theta. This is x. And this is y. And so what we end up finding out on the unit circle is this is the cosine of theta, this angle here. And this is going to be the sine of theta, that angle there. So what we're going to do, we're going to look at trigonometric identities. We talked about angles. We talked about different circles, unit circles. How to convert between radians and degrees and radians. And we're going to take a look at trig identities. So the trig identities, ultimately what they let you do is they can help you find the trig function values for angles that are not 30, 60, 45, 90, and so on. You can find, say, for example, the sine of 15 degrees. You can do something like that. For example, we know that the sine of 45 degrees is rad 2 over 2. And then the sine of 30 degrees is, let's see, 1/2. So what about the sine of 15 degrees? So we can use a trig identity. We're going to look at one approach of doing this that lets us find the sine of 15 degrees. So that's one use of trig identities. It lets us find the trig functions. In this case, the trig function is sine. So let's say we want to find the sine of 15 degrees. We know the sine of 45 and the sine of 30. We're going to be able to find the sine of 15. And we'll look at that in a little bit. So trig identities let us do that. The other thing they're going to help us out with is when we get into calculus, especially when we're dealing with integrals. We're going to have, for example, power-reducing trig identities. They're going to make our lives much easier when we have to do integrals. We're going to have some integral formulas, like what's the integral of the sine of theta? What's the integral of the cosine of theta? And the sine squared can get a little tricky. We're going to do the integral of that. So we'll have some trig identities that will let us convert a sine squared into a sine of something else that we can take the integral of. So that's going to be massively important. And that's a trick they use in this textbook a lot. You'll see the power reducing trig identity. For example, cosine squared into the cosine of something else, or sine squared into the sine of something else. But we don't have that power anymore. That exponent's gone. This textbook does that a lot, all the way through Calculus 3. That's a trick that they use. So that's definitely something that's going to help. So trig identities for us, so far, at least in trigonometry, it would let us find the sine function, say, of like 15 degrees when we know the sine of 45 and the sine of 30. And again, I'll show you how that's going to be done. On the other side of things, though, for calculus, is going to let us turn like sine squared into cosine squared into a sine or a cosine that we can take the integral of. So we're going to have this new benefit from trig identities that we didn't have in trigonometry. So let's jump into these, and we'll revisit the sine of 15 degrees. So let's say we have this. So the height is y, and the base is x. Now, in this case, though, r, we don't know if it's equal to 1. So we got to be careful, x is cosine of theta. Not necessarily. That's only if r is equal to 1. So we're going to have to use our definition for sine and cosine here. Cosine of theta is the opposite, adjacent over the hypotenuse. Or in this case, this is your adjacent, that's your hypotenuse, x over r. Cosine theta, x over r. Let's solve for x. So what we're going to get is r cosine theta is equal to x. Now again, if this is the unit circle, r would be equal to 1. 1 times cosine of theta is just cosine theta. So that's our cosine theta is equal to x. Now for y, is what we're going to do. We're going to take the sine of theta. Now sine of theta is opposite over hypotenuse. Or in this case, it's going to be y over r. Again, if we solve for y, r sine theta is equal to y. Now, if you take a look at that triangle in the circle, it forms a right triangle, something like roughly like this. So by the Pythagorean theorem, well, what we're going to get is x squared plus y squared is equal to r squared. So this squared plus this squared gives us that squared. Now, x is r cosine theta. Y, r sine theta. Also r. And r in there. R. Now, we're going to talk about this later today, but we're going to distribute these exponents. We get r squared cosine squared theta, r squared sine squared theta is r squared. And then what we're going to do is factor out r squared. So what we're going to do here, we're going to make not much of an assumption, to be honest. We're going to divide both sides by r. And of course, we're going to assume that r is not equal to 0. Well, you really can't have a triangle with a hypotenuse of 0. So this isn't so delicate. And so what this will give us, cosine squared theta plus sine squared theta is equal to 1. Very important identity. Very important identity. So for this, there's some other things you can do with it. If you divide by cosine squared theta, you're going to get another identity. You're going to get that. So if you divide everything by cosine squared, you're going to get this. Or if you take this, divide by sine squared. You're going to get that. So these are the Pythagorean identities. We start off with this, we derive it from the unit circle, or actually a circle of radius r, not necessarily a unit circle, though you could. And then if we take this and you divide it by cosine squared, divide everything, you're going to get this. Or if you take this and divide by sine squared, you're going to get that. And so these are the Pythagorean identities. And these come up in calculus. These are, especially to get into trig substitution. I think this one is kind of a popular one that comes up. All right. Now, we come to the sum and difference formulas. Now, the thing with trig identities is that there's a bunch of them. So it doesn't hurt. They should have a reference in the textbook. Let's take a look here where that's going to be. Let's see here. So if you turn the book, the back inside cover, this page here got a good collection of trig identities. Let me see, do they have everything? Looks pretty good. It's a good collection of them. So this is a reference, especially if you're working on homework problems, especially when you get to integration. Being familiar with this won't hurt. All right, just knowing where it is and looking at it. All right. So the next group I want to go over. So those are your Pythagorean. Next, we have our sum and differences. Now, these I'm not going to derive. If you want to see a derivation of them, a book I do recommend, I don't know if you use this book or not, there's a very good derivation in this textbook for sum and difference. And once you come up with the base formulas, it's pretty easy to come up with everything else. And you can come up with a lot of stuff using sum and difference formulas. If you want, I could go through this derivation at some other point or post some notes on how this is done. But this is something that I do recommend taking a look at this text. They have a great derivation for sum and difference. So first one for sum. So I'm using the formula from that other textbook for the notation. So you have two angles, A and B. So if you want to find the cosine of the sum of those two angles, this is how you would do it. Or if you want to find the sine, so this is what you're going to get. So these are your sum formulas. Now to come up with the difference formulas, what we can do is this. Well, this is going to be the cosine of A plus negative B. Again, we're going to write subtraction as the addition of a negative. We have cosine A, cosine of negative B, minus the sine of A, sine of negative B. Now, this is another identity I'm going to mention, but if you take the cosine of a negative, the negative goes away. And you can think of cosine in this regard as behaving like an even function. But sine behaves like an odd function. So that means this is going to pass through. So this negative will come out, it'll hit this minus sign. You're going to get this. So this is going to be your cosine of A minus B. Now, what about the sine? And that was the question we asked at the beginning of class. We had the difference of two angles. We want to know the sine of it. So same idea. All right. So again, the cosine of a negative takes out the negative, goes away, behaves like an even function. Sine of a negative, it's going to be like an odd function. It's going to come through. So we're going to get this. The sine of A, cosine of B, minus, because this will come on out, cosine A, sine of B. So now we can figure this, what's the sine of 15 degrees? We can do that. And this is how we do it. Just double checking, making sure that looks good. All right. Okay. 30. Okay. 45 and 30. Now we saw that the sine of 45 is rad 2 over 2. And the cosine of 30. Now the cosine of 30 in this case is going to be rad 3 over 2. Well, it's always rad 3 over 2, but it's a little bit of information we needed from before. We didn't have before. And highlight. We did have this. So now we're going to do the multiplication. So 4 root 2 root 3 minus root 2 over 4. And turns out, and we'll talk about this when we get the exponents, when we multiply these roots, we'll get 2 times 3 over 4, root 2 over 4, or root 6 minus root 2 divided by 4. This point is this. We didn't actually have anything on the unit circle that told us anything at all about the sine of 15 or the cosine of 15 degrees. But because we know the sine and cosine of 30, 45, and 30 degrees, or the cosine and sine of 45 and 30 degrees, we can use this trig identity to rewrite the sine of 15 degrees in terms of things that we know. And then plugging in the values for what we know, we can get a sine of 15 degrees. So that's what we've done in trigonometry with trig identities. For calculus, again, we have another application for these, is it's going to make our problems easier. And so that's going to be really helpful. Again, when we get to integration, that's going to be a huge help. So there's your sum and difference formulas. So double angle. We've got that. So here are your double angle formulas. There's a couple others that are going to be really useful. And this is what I'm going to be getting at about that power reduction. We also have 2 cosine squared theta. Let's see. It's 1 plus cosine 2 theta. Double check that one. Okay. So this is going to be extremely helpful when we get into, again, integration. We're going to have formulas for integrating the cosine of some angle and then the sine of some angle. It's a little trickier to do cosine squared. So what we can do, instead of trying to integrate cosine squared, we're going to integrate this instead. So that's something we can do. Another one that's going to be helpful. And again, we're reducing the power on this thing. And that's going to be really helpful in calculus. So these are your double angle formulas. For your half angle, now this is a big one. And really it's just a version of the last two double angle formulas we just saw. It's just written a little bit differently. So that's going to be your half angle formulas. Another way of thinking about these, you could also think of them as like this. So that's another way of thinking about them. And I know this one, these two do come up a lot. I always use them in Calc 3 homework problems. So again, just kind of be aware that these are here. If you find yourself with a cosine squared or a sine squared, you need to get rid of them. And the cosine and the sine are going to be all right. This is one way you could do that. So, any questions about that? So even on. So this one, cosine of negative theta is the cosine of theta. Likewise, let's see, secant of negative theta is the secant of theta. Then the sine of negative theta is negative sine of theta. That's what was going on in that derivation with the sum and difference formulas. So if you have negative b, that's what was going on there. And then likewise, your cosine of negative b, we just had the cosine of b. So that, again, that's what was going on in the sum and difference formulas. So cosine negative theta is just cosine theta. Secant, which is actually just 1 over cosine. Secant of negative theta is secant theta. Sine of negative theta is negative sine theta. And then cosecant, which is 1 over sine, and then same with tangent. And cotangent, because they both contain sine functions. We'll look at that in just a little bit too. So these are your even and odd. All right. So the reciprocal or ratio identities. Secant of theta is 1 over cosine theta. Or put another way, cosine theta is 1 over secant theta. Cosecant theta. 1 over sine theta, or sine theta. 1 over cosecant. So tangent is 1 over cotangent, and then cotangent one over tangent. So, excuse me, those are your reciprocals. For ratios, tangent is sine over cosine, and then cotangent is cosine over sine. So any questions about these identities? And these two, for tangent and cotangent, are very key. These are going to be really important. So, and these do come into play throughout the course and throughout the textbook. So those are your reciprocal and ratio identities. So next, I just want to talk about triangles. And these are just formulas we can use to help solve triangles, or find the lengths of the sides, find the angles on the inside. And the Pythagorean. So again, that means 90 degrees. It means we're dealing with a right triangle. So a squared plus b squared equals c squared. All right. Now, other things with triangles, we're not just limited to right triangles. We can actually solve other triangles using different rules. Law of cosines. And when you get into dot products, they have two formulas for the dot product. You don't really get in those till Calc 3, though you do cover them in the trigonometry, at least the trigonometry at this campus. But you actually use the law of cosines to prove one of the really interesting formula for dot products. But that's for another time. All right. So let's say you have side C, A, B. And this is angle C. I'm going to give a little curly Q to say it's capital. This is angle A. This is angle B. So this is the law of cosines. C squared, A squared plus B squared minus 2AB times the cosine of angle C. Or A squared is B squared plus C squared minus 2BC times the cosine of angle A. Or B squared equals a squared plus c squared minus 2ac times the cosine of angle B. So for the law of cosines, you have these three different ways of, well, working with the law of cosines to try to find, well, the sides of these things and then the angles on the inside. So that's your law of cosines. Any questions about that? All right. So the other one is the law of sines. Let's see. Sure, that's good. All right. So the law of sines says this. You make that capital C. So that's your law of sines. And in a lot of these problems, when you're working with triangles that are not right triangles, you actually use combinations of the law of sines and the law of cosines to solve those triangles. So any questions about that? So one more fact about triangles. The last thing to mention with triangles, if you add up all the angles on the inside of a triangle that's on a flat surface, you're going to get 180 degrees. And that's pretty much what we use. This rule and then the law of sines, law of cosines, Pythagorean theorem. If we just have one triangle in front of us, we use those four things to try to solve the triangle. Solving a triangle means you're trying to find all the angles and the lengths along the sides. And now if you have two triangles that are maybe congruent or they're similar, we use ratios and other things we can do to make this easier. But if you just have the one triangle, you've got your Pythagorean theorem, if the triangle is a right triangle. You've got your law of cosines, your law of sines, and the fact that the angles on the inside, ooh, forgot an N. Those angles add up to 180 degrees. So that's pretty much it for triangles. Any questions about that? You're not going to really deal too much with those types of laws. Pythagorean theorem is going to be really important. Sum of angles to 180 degrees is going to be really important. Law of cosines and sines is used much less. So now here's something. That we didn't touch on at all in trigonometry. I've seen this come up before in physics, oddly enough. So when you have two inequalities that are used sometimes, and I think what's going to happen, one of these we're going to end up using really when we get to limits. It's going to be helpful. But the first one is this. And again, I've seen this used in physics. I've seen this part of it used before when trying to prove something in physics. So this one, I think again, it's going to come up when we get into chapter 2 with limits. There's also one that involves cosine. Now there's a great explanation as to why this is true in the text. It uses a little bit of subtlety. So if you have any questions about why these are true, let me know. There's a little subtle trick I think they use in the text here. The trick is that if you have a circle, this is theta, and this here is your arc length S, and this is your radius R. So a formula we have, S is our theta. But if R equals 1, then S will be equal to theta. So in the proof for these, the idea that S is equal to theta comes up. So just pointing that out, if you let R equal 1. All right. So those are some special inequalities. So finally, we're going to get to graphs of trig functions. So first off, trig functions are periodic. So what that means is that you have this distance called a period, and every time you travel the distance along the x-axis of the period p, the y values start repeating themselves. So what this means, if you have f of x, and then you travel p units down the x-axis, you have the same y value as f of x. So in other words, this is f of x, and likewise, this plus p. They're going to have the same y value. And this will repeat itself forever. So every p units, you're going to get this y value. So f of x plus p f of x plus 2p. Those are all going to have the same y value. Are all going to equal y. So this is what we call a function that's p periodic. Like it has this period of p. Now, trigonometric functions are periodic. They repeat the y values every p units. And depending on which trig function you're working with, they're actually going to have a different period. So for sine, cosine, cosecant, and secant, p is 2 pi. And then for tangent, cotangent, p is going to be pi. Now keep in mind, this is sine, cosine, secant, cosecant, tangent, cotangent, where we haven't modified them. We haven't done any stretching, we haven't done any displacements or anything like this. And we're going to look at how to do that. And there's a real slick trick for this that makes figuring out the period of a modified function really easy. You can actually make it really hard, you can make it easy. But for sine, cosine, cosecant, secant, the period's 2 pi. That means the function repeats its y values every 2 pi units. These functions, they're going to repeat their y values every pi units. So for sine, and I mentioned this in my trig class. The trig class, we usually think of sine of theta, and that x and y are the x is the cosine of theta, y is the sine of theta. We're going to switch over now. Instead of using theta, we're going to use x as the angle, and y is just the output of the trig function. So this can be a little confusing when you're dealing with the unit circle, unfortunately. Technically, what you should say if you're looking at your unit circle is y is sine of theta, where you have a theta axis instead of an x-axis. But I'm going to use this notation anyway. We're going to use x now as the angle. So what this looks like, and again, this is one of these canonical functions. And so these are sort of the canonical function values. So this is one period of sine. Now it's going to keep going. It's going to repeat itself. It's going to repeat itself. But this is one period of sine, 0 to 2 pi. And if you know your sine function, you actually know your cosecant function. It's a little lower. So if we draw in our sine function, there's a period of our sine function. If you want to do cosecant, which is 1 over sine, everywhere that the sine function crosses the x-axis, put a vertical asymptote. So once you've done this, every time the sine function contacts that x-axis, vertical asymptote, vertical asymptote, vertical asymptote. And then the draw in cosecant at the top of the sine function, between the asymptotes, put this sort of parabola-looking thing. The same thing here. At the bottom of the sine function, again, staying between the asymptotes, put in that little parabola. And so this would be one period of y is cosecant x. So you've got your sine x, and from that you can get your cosecant x. So questions about that? All right. So that's sine and cosecant. Another two that are related to each other is cosine and secant. And again, cosecant, just want to mention this, it's 2 pi periodic. So what's going to happen is we're going to get another upward parabola and then another downward one, and it'll keep repeating this pattern for every 2 pi units. Now look at cosine. So cosine is going to do this. Period of cosine is going to look like that. So this is sort of the canonical form of cosine of x. Now from this we can come up with secant. And again, what we're going to do, everywhere cosine crosses the x-axis, we're going to put a vertical asymptote. So let me get the cosine on here. And everywhere we cross that x-axis, we get a vertical asymptote. And just like sine, at the extremes of the cosine function, we're going to attach those parabolas. So this one will go between the asymptotes. Now this one, we actually can only do half. We have half a hill, so you get half a parabola. Half a hill, half a parabola. And so this is y is the secant of x. So that's sine and cosecant, cosine and secant. And again, these are sort of the canonical forms of these trig functions. Now they're going to repeat themselves every 2 pi units. We're going to see this complete itself and then have another full parabola and then another half, which will complete itself in the next period, and then so on. Keep going. So last ones, tangent and cotangent. Tangent's going to do this. That's your y equals tangent of x. Now what's going to happen is it has a period of pi. So unlike the others that had a period of 2 pi, this one has a period of pi. It's going to do something sort of peculiar. It's going to do this. It just repeats itself every pi units. So negative pi over 2, pi over 2, pi over 2, the 3 pi over 2, 3 pi over 2, the 5 pi over 2. The distances here are each pi units long. So that's what tangent's going to do. It's just going to repeat these little graphs on and on forever in the positive direction and the negative x direction. So that's your tangent. Cotangent cotangent is going to look like this. A little more depth here. And again, its period, it's going to be pi units, just like tangent. Though instead of going from negative pi over 2 to pi over 2, it goes from 0 to pi. And like tangent, it's just going to repeat itself. So just like tangent, this graph will just be copied all the way down the positive x-axis and all the way down the negative x-axis. So those are the canonical graphs for the trig functions. Any questions about that? All right, how are we doing? Okay. So it looks like we'll finish this section. We'll get into 1.4. I don't know if we'll get to 1.5, but that's okay. We're actually going to catch up on schedule, I think. So looking at transformations. The last thing with the trig functions before we get into inverses, we'll look at that in section 1.6. It's going to be transformations. And so what I'm going to do, I'm just going to work through an example with transformations. I'm going to show you some tricks. So let's say we have this. So we got to graph something like this. What I'm going to do first is I'm just going to graph sine of whatever's on the inside of the parentheses. So here's the idea. I'm going to just graph one period of this function. And to do that, we know that the sine is a period of 2 pi units. And the canonical version I'm going to use, which goes from 0 to 2 pi. So we need to figure out, well, if we do all this stuff to x, how does that change the period in terms of length and location? How's it going to change the length and location of our canonical period? So this is how we're going to figure this out. So that's the canonical period. It's 2 pi units long, and it's located from 0 to 2 pi. So what we're going to do is this. Inside the canonical period, because usually when we graph the canonical period, this entire thing is going to be x. So we're going to take this entire thing, And when this entire thing is just x or theta, it's between 0 and 2 pi. So we're going to take this entire thing and insert it between 0 and 2 pi. So the entire piece here, if we think of it as sort of like, instead of calling it 3x plus pi over 2, we call it just theta. Like this whole thing, which is called theta. Well, theta would be between 0 and 2 pi. But we can unmask theta and show that theta is more complicated. It's just 3x plus pi over 2. So let's solve for x. So if we subtract pi over 2 everywhere, it'll cancel here, and we subtract here and here also. That's how we work with these inequalities. Now we divide by 3. We divide everywhere by 3. So we're going to get this. Now, what is this saying? Well, our canonical period is from 0 to 2 pi. It's 2 pi units long. But this one is going to be from negative pi over 6 to pi over 2. Now, what we can do is we can figure out the other points. So for example, if you want to find the middle point here, take pi over 2, subtract negative pi over 6. We're going to get pi over 2 plus pi over 6. Multiply top and bottom by 3. We'll get 4 pi over 6. So that gives us the distance from here to here. And if you, let me get my little, there it is. If you reduce that, you'll get 3 pi, 2 pi over 3. And so this is going to be the period. Now, the key points on sine of x. So this is the period. This is the period divided by 2, period divided by 4, and the period at 1.5 the period, or sorry, 3/4 the period. So what we know is this. we found this. Oh, sorry, we found this one. We know this one. This is the negative pi over 6. This is the pi over 2. We still need these locations. So this is what we know so far. We know where it starts, we know where it stops, and taking the difference of these two, we get the period. So to get this one, take the period, divide by 4. Pi over 6. So what we're going to do, let's see, we got to be a little careful here because this is 0. So if we add period over 4 to 0, we just get period over 4. So what we have to do is take the start that's going to actually give us our period over 4. So what that means this next one's going to be 0. Now, an easier way you can actually do this, and this is going to kind of be a headache. So let me show you something else. We know the period is 2 pi over 3. It turns out that for the canonical, sine function, the distance between the points that we use, it's the same distance p over 4. So in other words, if you take the canonical sine function, I know I'm kind of dragging this out, but I just want to come up with a little easier way of doing this. The distance, again, this is the canonical sine, is pi over 2, pi over 2, pi over 2, pi over 2. The way you come up with this distance, take pi over 2, divide by 4. I'm sorry, 2 pi divided by 4. And that's how you come up with that separation. So if we take this period and we divide by 4, we're going to get the distance between the critical points or the important points on our sine function. So for us, P is 2 pi over 3. So we're going to take 2 pi over 3 and we're going to divide it by 4, and that comes out to pi over 6. So that's going to be our separation. So now when we go back to our function here, our graph, one, two, three, four, we've got our fours there. So what we're going to do is we're going to take pi over 6, add it to the start. We're going to get 0. Now for the next one, 0 plus pi over 6. Well, that's just pi over 6. Now for the next one, pi over 6 plus pi over 6 is pi over 3. And then if you just want to check to see if this is working, pi over 3 plus pi over 6 will be pi over 2. So once we figure out the width of the gaps between the critical points for a sine function, it's relatively easier to come up with our base sine. So let's see here. So we'll start, we'll max, we'll cross at the minimum, and then we'll stop. Whew. So there you go. So what this does, this takes that canonical form of sine, it actually shrinks it down. The period, again, is 2 pi over 3. So it's going to shrink this down. And the result is that, oh, let me see, period. Sorry, I didn't really, let me take a look real quick. I want to get that stated correctly. Yeah, it's 2 pi over 3. So it's 2 pi over 3 is your period. So we've gone from a period of 2 pi to 2/3 pi is what's happened. And then we shifted it over from 0 to 2 pi to negative pi over 6 to pi over 2. So that's what this part of it looks like. Now let's do this. Now we're going to vertically stretch this. So instead of going from -1 to 1, it's going to go from -2 to 2. So now we've got that. We're just going to stretch this thing vertically. Finally, we're going to add the 1. So we deal with this first. We put this between 0 and 2 pi. We find the actual period, its location, and its length. We can compute the period's length. It takes sort of the rightmost value of the inequality, subtract the leftmost. It's going to give you your period. And then what you can do, if you divide that period by 4, you can just take your starting point and then add to that until you get to the ending point. And that's going to give you the critical points for your function. Then we're going to take that function, do the stretch, multiply by 2 in this case. It's going to double the vertical size of this function. Finally, we're going to shift it by 1. Plus 1. We're going to get a vertical shift. So what this means is we're going to take this graph, we're going to shift it 1 unit. So instead of going from -2 to 2, we can add 1 to both sides here. This is along the y-axis. And so we're going to get -1 to 3. So instead of starting at 0, we're going to start at 1. And when you have 0 for x, it'll be 3. And then we're going to cross not the x-axis, but now the line y = 1. And then the bottom is going to be reached again at pi/3. That's going to return to y = 1 at pi/2. Like so. And so that's going to be your final graph. So the idea is that you can do this in stages. And I think the easiest way to do it, figure out your location and the width of your period, then stretch, and then vertically shift. So any questions about that? Let me look up one thing here. So the book, they give a different formula for this. Let's see. You have a slightly different formula. And I'm just a little hesitant because I think with the inequalities, I mean, granted, taking the way of computing the period is a little clunky. I'll admit that. And then coming up with those, dividing it by 4, that can be kind of clunky too. They do use a slightly different approach. So what the textbook will do for finding the period, you can take this, you can factor out a 3. And the idea is going to be this. If you distribute this 3, you'll get 3x. When this 3 gets multiplied to this, it'll cancel out with this 3, so you get pi over 2. We're going to get something like this. So this, you can see what's called a phase shift. I think the text handles it like this. Like so. And so what ends up happening two pi over the period p, they actually use the letter b, but that's what they do. This is equal to the number we factored out. So this is the period. So if you solve for p, you'll get p is 2 pi over 3. So that's the alternative way of finding the period. The other way is just take whatever is on the inside of your sine function, put a p between 0 and 2 pi, solve for x, and then take the difference between the rightmost term and the leftmost term. That'll give you the period as well. And then you can divide this by 4, and that's going to give you your increments along the x-axis. Now, similarly, you can graph like this for the other trig functions. For the sake of time, we'll skip it. So what I'm going to do, I'm going to step out for just a moment. I have to stop the recording. I'm going to go to a different computer.